Yeah, you just do it right after. Wait, it's the beginning. I still get 0 to. And you guys start. Oh, you're using the lower one. That's just for no, I don't use any of my zero. Okay. Yeah, because when I use
Okay.
1 through 3, with the term 0 and throw a negative over. So number that doesn't. That makes sense. It just returns. Okay. Yeah. Because like I said, like I wrote comments wait now slide 2, and it makes sense, but then it just gives me the wrong output. So it's exactly what I'm writing. But I guess they're just choosing your badge. Yeah. I know when you here. It's yeah. Oh, it's just printing on your shape. Yeah. And you don't use it, so you do. You have to put it as a 0 because when you go call go sign, it's gonna look at. You know, mine's like it'll always look at 0. I did read that. I read that. I think I just found it online. It's like whenever you're using like if you're calling anything, it's check. That's why it's I guess that kind of makes sense here. Oh, that's why you moved it into 0. Yeah. We move it to 0 and then we square it. Yeah, which is how we get it. Because it's a stack, right? So it can only yeah, and I can do and then you move it back into 10. Then you could do that with it. That makes sense. Or so you could call it. If you can call it from 0, yeah. That's gonna change. Lower it stuff. Yeah, it's I tried doing that to do work. I did. Oh. So you are you still in 10 through 13 for that side? So my sides, I guess 15, 13 for the side 1, side 2. This is for the angle is. Oh, I do you know about angles. 15 and 14 in that order. On the side 150. That's average. Yeah, so the sides are second, 13, 14, 15. Yes, is that better? If it was called it's the sun. It's your game. That's what just the start. If not, just delete that. Because I'm getting the sides first, right? Or it's starting at 13. That's something else, right? You said your sides are 13. No. So side 1's at 15. Oh, side 2's at 14. And the angle's at 13. Yeah. Okay. I don't get any compliment. Yeah, I just did it like there's something about here. The top down maybe it might not.
Okay, so
regardless, still calling the register.
I'm gonna put this out.
I look at a lot of orders, which is why I started this. I thought that's weird.
Okay, so we got that. Where did this come from? Okay. In an integer, there's left and right ends. That's not tech terminology. But an integer like 3,491, this one over here has more importance than the one. So that is the most significant, in this case, digit. In binary numbers, it'll be the most significant byte, but the principle is still the same. So this is the least significant digit. And I just write LSD, least significant digit, most significant digit. So it has to do with processing. Say this whole discussion is about numbers only, floats and integers. It doesn't apply to strings. There is no most significant digit in strings. M, S, D. Okay. So it has to do with what is the order of processing of numbers. Okay. In printed text, at least in some cultures, printed text reads left to right. Left to right. He has $382 to spend. Okay, so the brain sees that sentence, spend, S-P-E-N-D, okay, and processes it, the he, the has, and then comes to this number and processes the 3 first and the 2 is last. So that's the most significant digit is processed first, MSD. Okay. In a moment, we have to reinterpret that to be MSB for byte and LSB for least significant byte. Okay. When that kind of processing is in effect, we say the number is little, I said that wrong. When that processing is in effect, the number is big Indian. In what I just read, you read it in a newspaper, you read it in a book, your brain processes numbers big Indian style. In this case, 382 is input to the brain is input left to right. In fact, left to right is not a good thing to say. It's better to say input MSD first. And then obviously LSD has to be last. Okay. There are some countries in the world where processing to the brain goes the other direction. And then it keeps going this way. I don't know how their brain works, but if it really does come to the 2 first, then the mental processing is little Indian. This is little Indian. Okay, so
MSD, sir.
Us computer scientists, numbers on paper are nice. I mean, you read the Titan News and all these numbers are on paper, but we want to know about numbers in memory or numbers in a register. So in memory, let's put down a fake memory here. and it has an address, 11, 12, 13, 14, 15, and so on, 16. Suppose the number, okay, machines process in the order of indexing. So memory addresses from small to large. Oh, I see that. Hang on to click on here. So if a number 17.93 is in memory, in that order, then the processing will be, we're going to grab a hold of the 1 first, and then the 7, and then the dot, and then the 93. So processing is in this direction, and true, 1 is most significant. Most significant. I want to start saying bytes because that applies to us in programming. And this one is least significant byte. And the processing would be from most to least, and that's big Indian processing. Okay, what does that have to do with the price of ice cream? The fact is, computers don't do that. That's just, I made that up. Computers would store that number backwards. 39.71. So this would be address 21, 22, 23, 24, 25, and then there's some unknown stuff out here, higher beyond that. That is not 39.71, that is 17.93. Processing goes this way because of the indexing. The memory addressing goes from small to large. Processing, that number is in this direction, and it's written in Little Indian intentionally so that the processing will reach LSB first. LSB. And this one over here is MSB. Processing reaches LSB first. And consequently, it reaches MSB last. I'm aware that in the past history of computing, they had my computers that processed big Indian style, but that's not common today. I don't know where you find those kind of computers. In museums, perhaps. Modern computers process Little Indian style. All modern computers are Little Indian. Okay. And you can check your own. It'll tell you that put in the command ls CPU and scroll down a little ways, and it'll say this machine is Little Indian processor. You can confirm it yourself. Okay, in registers, the bits have numbers. RCX is a 64-bit register. And the 64 bits are numbered from 0 to 20, 0 to 63. It would be, to be in North American culture, we should number those zeros over here, 0, 1, 2, 3 to 63. But in textbooks, they never show you that. What textbooks will show you is a secret scheme along the bottom where bit 0 is here. What is it? And bit number 63 is here. And then you can take the number like $384.23, and you write it in there, and it looks like to human eyes that the big, most significant digit is first, because humans' eyes go this way across the page. And it looks like that, but it's not true. The machine follows the indexing, and it will go to the low index first and pick up the 3, and then the 4, and then the dot, and then the 4, and the 8, and the 3. So this is the machine order here. Okay, but of course it's not in decimal. It's going to be in binary, but it's the same concept. The least significant binary byte will come first, and it will be on this side of the register. What does that have to do with anything? One thing is, you might have noticed when I draw a picture of the stack, it's inverted. Bottom, top, RSP, pointer. It doesn't, that's the bottom quad word. It is drawn intentionally backwards so that if this quad word started at address 10, then that's the address of this corner, and the address of the next byte over is 11, and the next byte over, the address is 12, and continuing in right to left until it reaches 17, if I'm writing in decimal. 17, and then this corner back here would be 18. Okay, got it. So the stack is written backwards. We can put numbers in there on paper that look like it's a good valid number. 3,487. And the 3,000 is where it's supposed to be. But for the machine, the 7 is first. As long as you keep that in mind. Okay. Do we do that? Do we do Little Indian processing in the second grade or Big Indian? Nobody knows. That's a test question. 7, 8, 41 plus. When the little kid in the second grade is told to add 2 integers, where does the kid process first? Yes, he's processing Little Indian style without knowing it. The teacher teaches him that way. Okay, you figure that out. There's no, the stack is backwards on paper. This is all done as a teaching gimmick, and everything works fine. Let's go on. The author has a section on memory layout. Can I fit it in here? If this were all of memory, all 16 gigabytes of memory, then isolated near this is not top's not the right word. Up here is high memory addresses. And these are low memory addresses. There's a general abstract view of all of memory. This is the stack area. Oh, I like to draw like this. Stack. It's at the back end of all of memory. And then at the front end, well, in the lowest addresses is the operating system. And then next higher addresses has executable code. Executable code. The loader brings in your LinkedIn file and places it near the operating system, and then it places next to it .data. Did I do it right? Yes. Things you declared in .data section. And then it places things that you declared in .bss section. And then there's a gap in the middle. And this is generally referred to as heap space, as opposed to stack space. If you dynamically create a pointer to something during runtime, it will be added on to here. This is available for storage created while the program's running during runtime. Okay, the author has a nice clean picture made by, I'm sure, electronic equipment, and laid it out nicely. The stack is up here and it grows down this way as you push things. If you allocate with the new allocator, then the heap grows this way. And hopefully they never meet each other. If they did, the whole program freezes. It's over. Okay, you can see the nice picture in the textbook. It's better than I can draw it. Let's see. And then there's the end of the chapter 1, and then there's quiz questions. Quiz questions. Let's practice some of those next class meeting or next week. Okay, quiz question. Chapter 2. I think I'm supposed to say chapter 3. Yes, I am. Chapter 2 had Van Neumann architecture, and it has like big Indian, little Indian stuff. Chapter 3 is integers in binary. Okay, let's take, now, I can't, it's too unwieldy to work with a quad word. So this is just going to be integers in bytes. And then you have to let your mind expand to what you can do in bytes, you can do in 8 bytes. Okay, let's take a number like 118, 119 decimal. The standard algorithm says divide by 2 repeatedly and you'll find your binary number. So here, let's do it. Oh gosh, that's 59. The remainder is 1. 59 divided by 2 is 29. The remainder is 1. 29 divided by 2 is 14. Oh, the remainder different than 1. Okay. 14 divided by 2 is 7. Remainder is 0. 7 divided by 2 is 3. Remainder is 1. 3 divided by 2 is 1. Remainder is 1. 1 divided by 2 is 0. Remainder is 1. Now, at this point, any further divisions just lead to nothing, to zeros. we could keep going. What would be next? It'd be 0 divided by 2 is equal to 0 with remainder 0. And you do it again, 0 divided by 2 is 0, remainder 0. So we might as well stop the sequence. When you reach this thing, time to stop. So the answer is what you get by reading the remainders in backwards order. Is 0, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Now, I didn't count right. Let's take away working in byte. It should have eight of these. Let's just cross this one off. Okay, there's our number that was originally 119. How can you run a check on it? See, I couldn't do that for 64 bits. I'd have to 64 divisions, and it'd just go on unfeasibly long. Okay, so these have a position value. Starting in Little Indian over here, this was position 2 to the 0. And the next one is 2 to the 1. And the next one is 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7. Okay. So if you take all the 1 positions and add them up, we should get our original number back. Let's do it. 0 times 2 to the 7 plus 1 times 2 to the 6 plus 1 times 2 to the 5 plus 1 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 to the 2 plus 1 times 2 to the 1, 0. That is what? 64 plus 32 plus 16 plus 4 plus 2 plus 1. What is that? 64, that's 96, 112, 116, 118, 119. That's it. Okay, it's a check on that the algorithm works. Okay. So here we have it in 2 directions. You're able to convert decimal to binary and the reverse. Okay. So if you start out with this binary number, you do this stuff, okay, and you get the decimal answer at the end. If you start with the decimal answer, then you do all these divisions, and you end up with the binary answer. Okay. Now, unfortunately, that what I just showed you works on unsigned integers only so far. That's good for unsigned. Yes. Okay, we gotta expand it to signed integers. Okay. Ready? Anyone have a question? Unless you want some. Yes, that's right. Okay. Okay. So here's the plan. We take our 1 byte and bit number 7, which is over here, is going to be set aside apart from the number, and this is going to be the sign. Okay, so the sign will be 0 means plus, and 1 means negative. And then the rest of the number is over here as usual. 1, 0, 1, 1, 1, 0, 0. Okay, and we put a 0 here, and then it's a positive number. Okay. And if there's a 1 there, it's a negative number. 1, 1, 0, 1, 1, 1, 0, 0 would be a negative number. NEGPOS. Okay, so how do you convert from a negative decimal to a binary number and reverse it? Let's do it. Conversion. Oh, what should I pick? Negative 103 to binary. Let's see, what's the best strategy? Okay, we'll learn what we do is we will handle the 103 positive case first, and then we'll make the answer negative. So start with 103. Why do we have to do that again? 103 over 2 is 51. 51 over 2 is 25. I'll try to speed it up. So 2 is 12. Remainder 1. Okay, 12 divided by 2 is 6. Remainder 0. 6 divided by 2 is 3. Remainder 1. 3 divided by 2 is 1. Remainder 1. 1 divided by 2 is 0. Remainder 1. Okay. We can stop here. I think, yeah, now we read it backward.
The 6 do not have any remaining. 6 do not have remaining.
So we have that 103 is equal to 1110111. And there's 7 digits, which is okay, but I'm going to put a positive sign with this. And that makes 1 byte. Now, the algorithm, there is an algorithm that goes like this. To find out what negative 103 is, you take all these bits and flip them over and then add 1.
Professor,
1, 0, 0, 0, 1, 0, 0, 0, plus 1, 1, 0, 0, 1.
Professor,
And this is claimed to be negative 103. That's a conversion from the original problem was start with 103 negative and find its binary expression. And here it is. Now, how can we know if that's really true? Let's see. This is here it is. Here's the answer. This number up here had better be 103 because we did all the divisions by 2. Okay, so we have 103 plus negative 103. That had better be 0. Now, let's put it here. 0, 1, 1, 1, 0, 1, 1, 1. Where is it? It's right here. 1, 0, 0, 0, 1, 0, 0, 1. So if x in algebra, if x plus y equals 0, then y is negative x. Let's add these. You know how to add 1 plus 1. That adds up to 10 because we have no 2. So we have to go to the next digit higher, next number higher. So 1, there's little endian again. 1 plus 1 is 10, carry 1. 1 plus 1 plus 0 is 10, carry 1. 1 plus 1 plus 0 is 10, carry 1. You can see what's happening. Get a 10 and carry 1. Get a 10 and carry 1. Carry the 1. Add those two, you get a 10. Carry 1. Add those two, you get a 10. Carry 1. Add those two, you get a 0. And you carry 1, which is outside the register. The register keeps this, and that's kicked out. Actually, it goes into R flags, if you want to know. The operation was successful, but something abnormal happened. It lost data in the overflow sense. Okay, I don't want to discuss R flags now, but that's where it went. So the sum of those two numbers in the register is 0. So the second one is the negative of the first one. It verifies that the system works. So if you're asked to find a negative integer in binary, 593, you first work on 593. Then you flip all the bits of that answer to the opposite. That's called taking the complement, by the way. And then you add 1. And then you have the answer for what you really wanted. Okay. Now, it becomes impractical the larger the integer. If the integer gets to be 2,890 or something, it's impractical to do all those divisions, and then you need a calculator to help you. But in principle, you can see it happening with small numbers. Okay. Here was a small number, 103. You go through all those steps, and you come up with 103 is flip them over. That means take the complement from here to here, add the 1, and then you have the answer for the negative question. Comes from that. Let me see. Did I do? I mean, did I do that? He says I made a mistake. Oh no. Someone with sharp eyes caught it right here. 6 divided by 2 is 30. And then this has no effect here, no effect here. Okay, let's go back and fix that. Okay. At the beginning, 0, 1, 1, 1. No, what did I do here? Oh, you read them backwards. 1, 1, 1. This one right here should have fixed it in your notes. That's a 0. Okay. And then when we flip them all over, this becomes a 1. And then this is a 1. It didn't affect anything serious. It just affects that one bit. It will stay. I'll find it here. 103, 1, 1. That's a 0. But in the flip, it's the 1. You're adding 0 and 1 rather than 1 and 0. It still stays the same. Okay. Yeah, this was a wrong remainder. That's something bad happened. Okay. Okay. Isn't it supposed to be what? Okay. There's a question in the chat messages. We're starting with 103 and we're trying to convert it to binary. So it goes through all these steps and it ends here. And then you read your answer. By the way, there's only 7 of these. 1, 2, 3, 4, 5, 6, 7. So I'm covering up the 0 here. And then you write 1, 1. Should I do it again? We're off by 1 bit. Yeah, the chat message person has it right. Okay. Now, you got when you play this back, you want to see it correctly. So here we got to do it right. Start. Negative 103, 2 binary. Okay. We're gonna. I'll okay, and you keep this going. Dot 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 dot, and you come to the critic, and so there's a remainder R1, remainder R1, remainder 0, 3 1s and a 0. Then there's 6 divided by 3 gives 3R0, and then 3 divided by 2 gives that. Okay, then 3 divided by 2 gives 1 R1, and then 1 divided by 2 gives 0 R1. Okay, and then that's far enough. We pick up 7 bits. And then you write 103 equals, reading upward, it's 1 1 0 0 1 1 1. But we have a 7-bit register. We have an 8-bit register. We had a 0 here. Okay, and that's a total of 8. Then we're going at the target is 103 negative. So we flip homes. That's complement. One, zero, zero, one, one, zero, zero, zero. Then add 1. And it's 1, 0, 0, 1, 1, 0, 0, 1, which is negative 103. All right, I think we're good. Now, the check, we'll do the check. This is 103 and this is negative 103. Let's line them up for addition. 0, 1, 1, 0, 0, 1, 1, 1, plus 1, 0, 0, 1, 1, 0, 0, 1. They're all going to cancel each other, by the way, just like in the previous one. So little Indian style, you start over here, 0, you carry 1, 0, and 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 you carry 1, 0, carry 1, 0, carry 1, 0, and 1 overflows. This is kept in the register, and this one goes off to our flags. And it's something exceptional happened. Numbers are not supposed to overflow, but when they do, R flags is informed that something happened. Okay, so the two add up to make a 0 in the 1 byte register, and everything is okay. What's our clock saying? We are at 10:44. Let's get the last piece in for today. Okay, there's a three-way conversion here: decimal to binary to hex, or hex to decimal to binary. We want to go 3 sides of the triangle. So the hex system is written 0, 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 8, 2, 2, 2. Yeah. And we're out of digits. Okay. Now, let's count in binary next to each one. You can see it increasing by 1 with each step down the page. Okay, that's very common sense. Okay, so we had a number back here. Here's 103, and here is negative 103. I'm going to copy those to the next page. Yeah. So 103 we computed was 0, 1, 1, 0, 0, 1, 1, 1, 3, 0, 0, 1, 0, 0, 1. Okay. So I frequently subconsciously put the little blank space in separating groups of 4. It's because you read a group of 4 bits, it fits in one of these over here. There's only 4 bits in use, and that's every combination of 4. So off the table, we could read that 7 is 0, 1, 1, 1. And off the table, it was right next to it, it's a 6. And over here, that's a 9. Why is it 2 9s again? Okay, it's just the way it is. Okay, so the first number is 67, and the second number is 99 for hex in a 1-byte register. Now, humans will read 67 and not know that it's hex, and so the standard notation is 0x67. And here it would be 0x99. It's the 0x has been around for decades. It simply means that what follows is written in base 16. That's in base 16, that's in base 16. Without the 0x, it's assumed that it's in base decimal. Okay, then, okay, so no matter what your number is, you can make it converted into hex quite readily. What would this be? 1, 1, 0, 1, 1, 0, 1, 1. So this is a one-word register. A one word has 16 bits in it. Okay. And that's a standard integer number. It happens to be negative because of this guy. But we would make it as equal to 0x. Now that's a D by itself. That is a 11. That's an A. So A. And that's an F. And that's a 3. Okay, I think I did that right. The 3F. 8 and 2 is 10, 11. No. And that's a B, everybody. How do I do this?
It's B.
Let's take it again. 1100 is C, so one more would be D. That's a D. That's okay. That's 8 plus 2 is 10, and one more is 11. This has to be a B. So it's 0x D B F 3. There we are. Final. Let's see, what else do you have to know? Oh, yeah, the complements. Whether you write it in binary or hex, it's still a two's complement system. What we've been studying right here, the last 35 minutes, is the name of the system of these integers is called two's complement. If the leftmost digit is not the sign, it's just part of the ordinary number, then it's called unsigned integers. Got it? So this one over here, if that's doesn't count as a plus or minus sign, it's just part of one big number, then the whole system is called unsigned ends. If that counts as 0 for positive, 1 for negative, then the system is called two's complement integers. Okay, so it's kind of neat. It doesn't matter which base you write it in, 2 or 16, the complementing still works. So let's conclude today with this 0 complements with F, 1 complements with E, 2 with D, 3 with C, 4 with B, 5 with A, 6 with 9, and 7 with 8. So 7 has complement 8, 8 has complement 7. They form pairs. The complement of C is 3, the complement of 3 is C. Well, let's suppose you have a hex number. X. D. That's a D. And this one's a 0. Okay. That's Manually, that'll take a long time. It'll take 20 minutes to figure that out. With a calculator, you could get the number quite easily. But we want its negative. So to go to the negative, we complement each digit, each hex digit. 4 on the table back here becomes a B. 9 on the table becomes a 6. A becomes a 5. 3 becomes C. D complements to 2. F becomes 0. 0 becomes F. And B becomes a 4. That's the complement of the starting number. But it's not the negative. The negative you get by adding 1. And then it's 0, X, B, 6, 5, C, 2, 0, F, 5. This is the negative. Okay. I don't know. That to, what are you saying, Hamid? Did I write it wrong? Oh, that's the old problem. Little b and big B, these are case neutral. Your machine will accept the hex letters in either uppercase or lowercase. You pick whatever you like. That's how you find the negative of a huge number. So how big are addresses? ADDRES. Addresses are 64 bits. It takes 4 bits to make a hex digit. So you divide 4 into 64. There are 16 hex digits in an address. By the way, the 16 hex digit address space is not anywhere near full. 15 years ago, they were using 32-bit addressing, and it filled. That 32 bits is around 4 billion. Okay, that's just 4 gigabytes. They could only address 4 gigabytes of RAM at a time, and that led very rapidly to the 64-bit machines we use today. So everything went 64. The registers went to 64. The addresses went to 64. The data path in the bus transmits 64 bits at a cycle. Everything went to 64 then, but with 64 bits, we aren't near filling it all up. We'll do some programming where we dump the addresses, but it will start out with 3 zeros, 3 hex zeros, and then some numbers. F, B, 8, 9, 4, 2, 6, 3, 7, B, F, 0. So there's 16 digits, and 16, each one represents 4 bits. That's a 64-bit number. This is the issue here. Machines are not anywhere close to filling up the addresses that are available. I think it's going to be another 20 years or more before they have terabytes or petabytes of RAM. Then they'll eventually fill up these address spaces here. But that's where we are now. Okay, everyone, it looks like it's 10:59 on the clock. You do a lot of programming this tonight. Have it ready in 6 days. And I lecture on textbook material while we're waiting for the next assignment. When you get the next assignment in your hands, then I'll lecture on things relevant to that assignment. And then after that, we'll come back to the textbook. Any questions? Okay, have a great afternoon, everyone. I stay here until about 11:45. Do what you need to do. We're done.